Now we shall discuss about errors in electrodynamometer wattmeter. Errors in Let me list out the errors which are present in electrodynamometer wattmeter. Error due to pressure coil inductance. Error due to pressure coil inductance. Error due to pressure coil capacitance. Error due to mutual inductance effects. Errors caused errors caused because of connections. Eddy current errors. Stray magnetic field errors. Stray magnetic field errors. Errors caused by errors caused caused by vibration of moving system. Vibration of moving system. And the last one is temperature errors. These are the errors which are present in electrodynamometer wattmeter. Coming to the first one, now we'll look into the error due to pressure coil inductance. Error due to pressure coil inductance. First, let me draw the dynamometer wattmeter circuit. In electrodynamometer wattmeter, you're going to have current coil and pressure coil. Current coil is connected in series with the load. This is the current coil which is connected in series with the load. Phase, neutral. Let V is the applied voltage. That V is the applied voltage. Pressure coil. This is the pressure coil. And you are going to have resistance in series with this pressure coil to limit the current which is flowing through this pressure coil. Okay. Now the combination of pressure coil and resistance which is connected in series with the pressure coil is called pressure coil circuit. This is pressure coil circuit. Okay. This is pressure coil circuit. Okay. V is the voltage which is applied across this pressure coil circuit. Okay. Current coil is connected in series with the load to carry the current which is flowing to the load. Pressure coil circuit is connected across the applied voltage. Okay. Let IC is the current flowing to the current coil. Okay. This is what? This is current coil. This is pressure coil. Let R is the resistance which is connected in series with the pressure coil to limit the current which is flowing to the pressure coil. Anyhow, this pressure coil circuit carries the current which is proportional to the applied voltage. Okay, let I is the current flowing to the load, I or IL. Now here IC and I both are equal. Let IP is the current flowing to this. Let IP is the current flowing to this pressure coil. Right. Now let me draw the pressure coil circuit. You're going to have a pressure coil circuit like this. Right. This is what this is R, and this pressure coil is having resistance as well as reactance. Okay, so let Rp is the resistance of this pressure coil. Okay, so let Rp, let small rp is the resistance of this pressure coil. Xp is the reactance of this pressure coil. Okay, so Rp is the resistance of this pressure coil, Xp is the reactance of this pressure coil. Okay, Rp, what is Rp? Rp is the resistance of the pressure coil, resistance of pressure coil. L, L is the inductance of pressure coil, pressure coil. Xp is the reactance of pressure coil. You can also write Xp. Xp is the inductive reactance, reactance of pressure coil. R, R is the resistance, resistance in series with pressure coil, in series with pressure coil. Next, Rp, Rp is the total resistance of pressure coil circuit, total resistance, total resistance of pressure coil circuit, coil circuit, which is equal to Rp plus R. Okay, total resistance of the pressure coil is Rp plus R. Okay, then V, V is the applied voltage, voltage applied, applied to pressure coil circuit. coil circuit. I is the current flowing through the load, or I is the current in the current coil circuit. Current coil circuit. Next, IP. IP is the current in the pressure coil circuit. Okay. Now, what will be the impedance of this pressure coil circuit? Now, the impedance will be ZP. ZP is equal to, you can take magnitude under root of RP plus R whole square plus XP square. Okay, where XP is what? Omega L. Right? Okay. Case 1 is, if the pressure coil circuit is purely resistive in nature. If it is purely resistive in nature, what will be the power measured by the wattmeter? Power measured by the wattmeter will be true power. Okay. You know, TD is equal to IPI cos of angle between IP and I dm by d theta. Okay, theta is equal to IPI cos of angle between IP and I dm by d theta by Kc or K. Okay. Now let us draw the phasor diagram if the pressure coil circuit is purely resistive in nature. Okay. Anyhow, now let me draw the wattmeter circuit. Anyhow, this is current coil which is connected in series with this. Sorry. Current coil in series with the load. Pressure coil across the applied voltage. Let V is the voltage applied to the circuit. Phase neutral. Now I am considering pressure coil circuit is purely resistive in nature. Okay, if it is purely resistive in nature, this will be the circuit for dynamometer wattmeter, right? Okay, the current which is flowing through this I, the current which is flowing through this IP. Now let me draw the phasor diagram. Okay, this is I. For lagging loads, current lags voltage by an angle phi. Okay, so this will be what? This will be V. If we neglect the voltage drop across this current coil, applied voltage will be equal to voltage across the load. Okay, so V is equal to VL. Now voltage leads current by an angle phi, or current lags voltage by an angle phi for lagging loads. Okay, then the phase angle between these two will be phi only, right? Okay, now if I consider this pressure coil circuit purely resistive in nature, if the pressure coil circuit is purely resistive in nature, then this voltage and the current which is flowing through the pressure coil circuit will be in phase. Both will be in phase. Okay. If it is purely resistive in nature, then this will be what? IP. Now you can have theta is equal to IPI by K cos of angle between IP and I, right? Okay, what is the angle between IP and I? Phi, cos phi, dm by d theta. Okay, now anyhow IP will be equal to what? V by RP. As it is, if RP is the resistance of this pressure coil, okay, then IP will be equal to V by RP. Then I by K cos phi dm by d theta. Okay, so here theta is direct proportional to VI cos phi. Okay, this is true power. That is theta is direct proportional to AC power. Okay, this is true power. True power. Okay, if the pressure coil circuit is purely resistive in nature, then you can measure true power. It is somewhat difficult to make this pressure coil circuit purely resistive in nature, but at least you make this circuit as resistive as possible. Okay, at least if it is highly resistive in nature, then you can reduce the error due to pressure coil inductance. Okay, so at least you make this pressure coil circuit as resistive as possible. So it should be highly resistive in nature. It should be highly resistive in nature. Okay. Now coming to case 2, if I include the effect of inductance, what will be the power? Okay. Now you're going to have the circuit diagram for dynamometer wattmeter. So current coil, pressure coil, R is resistance in CC. Load. Okay. Right now let me draw the phasor diagram. I for lagging loads, current lags voltage by an angle phi. So this is V. Current lags voltage by an angle phi. Okay. IP is the current flowing to this. Okay. Now, how can I draw the phasor IP? By including the inductance of this pressure coil. Okay. Now, anyhow, this will be inductive in nature now. Okay, if it is inductive in nature, current lags voltage. V is the voltage across this pressure coil. Then current lags voltage by some angle. Okay. Anyhow, let me consider this inductance value is somewhat less only. Okay. Then angle between voltage and IP will be small. Okay. So let this is what this is IP. Let beta is the angle between V and I. Let beta is the angle between V and I. Okay. Now theta is equal to IPI by K cos of angle between IP and I dm by d theta, right? Okay. Now what is the angle between IP and I now? Okay, you do one thing. Let phi dash is the angle between these two. Okay, then which is equal to IPI by K cos phi dash dm by d theta. What is phi dash? Phi dash is equal to phi minus beta, right? Okay, then which is equal to do one thing. In place of IP, you write V by ZP after including the effect of inductance. IP will be equal to V by ZP. I by sorry I by K cos, what is phi dash? Phi dash is cos of phi minus beta dm by d theta. This will be theta. I'll do one thing. Anyhow, you know theta is directly proportional to AC power. Okay, AC power. So anyhow, this will be the actual reading. Actual reading measured by the wattmeter after including the effect of inductance. So you take this as measured value, measured power. Sorry, measured power. Let me take this as true power. Okay, anyhow, theta is directly proportional to power, right? Okay, theta is directly proportional to AC power, right? Okay, so anyhow, VI cos phi is true power. Okay, theta is directly proportional to VI cos phi. Theta is directly proportional to AC power. Okay, so I am treating this as true power because theta is directly proportional to AC power, right? Now, what is the ratio of true power to measured power? True power is I, sorry, this is what V I cos phi by Rp dm by d theta by what is measured power? Vi by Zp. Okay, K also, right, into K cos of phi minus beta dm by d theta. Okay, which is equal to cos phi by cos phi by into Zp by Rp into cos of phi minus beta. Okay, we know what is this, right? Zp is equal to Rp by cos beta. Okay, from impedance triangle, you can draw the impedance triangle. Rp, and you are going to have Xp. This will be what? Zp. Okay. The angle between these two will be beta. Okay, from this you can have Zp is equal to, or cos beta is equal to Rp by Zp. Okay, so cos phi by cos beta is equal to Rp by Zp, right? So cos beta into cos of phi minus beta. The ratio of true power to measured power is equal to This is the power which is indicated by the wattmeter. Actual power indicated by the wattmeter is measured power. Actual power to be measured is true power. Cos, sorry, cos beta. Cos of phi minus beta. Okay. This is nothing but correction factor. Okay, correction factor. CF, correction factor. For lagging loads, this is the correction factor for lagging loads. Okay, then correction factor for leading loads will be cos phi by cos cos beta, cos of phi plus beta for leading loads. Okay, y plus here current leads voltage by an angle beta. Okay, if you draw the phasor diagram, then you will get to know that. Okay, angle between I and LP will be phi plus beta. Otherwise, let me draw the phasor diagram. Okay. Okay. Current leads voltage by angle phi. This will be what? This will be IP. This current lags. Anyhow, as it is inductive in nature, pressure coil circuit is inductive in nature. IP lags V by an angle beta. Then the angle between these two will be phi plus beta. For what? This is for leading loads. Leading loads. Okay. Now correction factor, that is PT by PM, is given as cos phi by cos beta into cos of phi minus beta, which is equal to cos phi by cos beta into cos of a minus b, means cos a cos b plus sin a sin b, right? So cos a cos b plus sin a sin b, which is equal to cos phi by cos beta we bring these two terms out, then you're going to get cos square beta cos phi into 1 plus tan phi tan beta. These two will get cancelled. Then you're going to get secant square beta by 1 plus tan phi tan beta. So which is equal to 1 plus tan square beta by 1 plus tan phi tan beta. Okay. Anyhow, beta is somewhat small value. Okay, if beta is small value, means tan square beta will be very small value. Okay, that is tan square beta is far less than 1. Okay, then you neglect this term. If you neglect the term, pt by pm will be equal to 1 by 1 plus tan phi tan beta. Okay, now What will be the percentage error? Percentage error is equal to measure value minus true value by true value into 100, which is equal to measure value by true value minus 1 into 100. Okay, you know, you have the ratio of pt to pm. What will be the ratio of pm to pt? Will be 1 plus tan phi tan beta. Okay, so this will be 1 plus tan phi tan beta minus 1 into 100. This is what this percentage error. Okay, so percentage error will be is equal to tan phi tan beta into 100. Okay, this is a percentage error. Okay, now what will be the error? Error is equal to measure value minus true value. Okay, which is equal to now, you know, what is measure value? We have the ratio. I'll do one thing, I'll write over here. Pt by pm is equal to 1 by 1 plus tan phi tan beta, right? Okay, then 1 plus tan phi tan beta into pt is equal to pm, right? Okay, then measure value will be 1 plus tan phi tan beta into pt minus pt, which is equal to, you're going to get tan phi tan beta into pt, which is equal to tan phi tan beta into what is 2 power? 2 power is va cos phi. Okay, then you're going to get error. You're going to get error is equal to vi sin phi tan beta. So this is error. This is the error due to the presence of inductance in the pressure coil circuit. Now coming to the compensation, how can you eliminate that error due to the pressure coil inductance? Okay, next one is compensation. Compensation for inductance of pressure coil. Inductance of pressure coil. Let me have the pressure coil circuit. Let Rp is the resistance of this pressure coil circuit, total resistance of the pressure coil circuit, right? Okay, now here what we do is, in order to compensate the inductance of pressure coil, okay, in order to compensate the inductance of the pressure coil circuit, we place capacitor across some portion of series resistance. This is series resistance. This is series resistance R. Okay, across some portion of series resistance, we place capacitor. Okay, we place capacitance. See, let R is the resistance of the resistance of some portion of the resistor. Okay, series resistance. L is the inductance of this pressure coil. Okay, now let us find total impedance of the circuit. Okay, Zp is equal to, you know, total resistance of the pressure coil circuit is Rp. Then what will be the resistance from here to here? Will be Rp minus R. Rp minus R plus j omega L plus what is the impedance of this parallel combination? Okay, R into 1 by j omega C by R plus 1 by j omega C. Okay, then you're going to get Rp minus R plus j omega L plus R by 1 plus j omega RC. Let me rationalize this. Then 1 minus j omega RC into 1 minus j omega RC. Then you're going to get Rp minus R plus j omega L plus R minus j omega R square C by 1 minus, okay, minus j square means plus, you're going to get plus 1 plus omega square R square C square. Okay, anyhow, omega square C square R square far less than 1 for power frequencies. It is less than 1, far less than 1 for power frequencies. At power frequencies, it is far less than 1. So, let me neglect this term. Okay, so if I neglect this term, you are going to get Rp minus R plus j omega C plus R minus j omega R square C. Okay. So now, Zp after neglecting that term approximately equal to that. Okay. So, um, to nullify the effect of this inductance, okay, we make imaginary part equal to 0. If I make imaginary part equal to 0, then you are going to get C minus, sorry, this is L, right? This is L. Okay. L minus C R square is equal to 0. Then L is equal to C R square. So the error caused by pressure coil inductance is almost completely eliminated if I make L is equal to C R square. This is the required value of capacitance. Okay, required value of capacitance is equal to L by R square. Okay, so that I can eliminate the effect of inductance in the pressure coil circuit. Coming to the second error due to pressure coil capacitance. So this is the error due to the presence of capacitance in the pressure coil circuit. Okay, you're going to have the pressure coil circuit like this. This is series resistance which is connected in series with the pressure coil to limit the current which is flowing through the pressure coil circuit, right? Okay, so this is series resistance. Okay, this series resistance may possess capacitance. Okay, that capacitance is nothing but interturn capacitance. That is capacitance between two turns. Okay, okay, that this is series resistance. Okay, then capacitance exists between any two turns of this series resistance. Again, between these two turns, again capacitance. Okay, between these two turns. Okay, between these two turns. Okay, so you're going to have capacitance like this. So interturn capacitance. Okay, so this is the error due to interturn capacitance. Capacitance between any two turns of the resistance. Okay, so this effect is opposite to the effect of inductance. Anyhow, this effect is this possess capacitance between any two turns. This capacitance is called interturn capacitance. Okay. Anyhow, this capacitance effect is opposite to the effect of this inductance. Opposite to the effect of this inductance. Okay. So for lagging loads, a wattmeter may read more value than the actual value. Okay. Anyhow, in most of the cases, this inductive reactance is more than capacitive reactance. Okay. So this error is less only. Coming to the next one. Next error is error due to mutual inductance. Mutual inductance effects. Okay, you have current coil and pressure coil. Okay, voltage coil. You place voltage coil, right? Pressure coil. Okay, otherwise let me draw like this. Voltage coil, pressure coil, right? Okay, this is the error due to the mutual inductance between these two coils. Okay, current coils and pressure coil. The mutual inductance between these two coils. Okay, current coils and pressure coil. Anyhow, at power frequencies, okay, at power frequencies, this error is less only. This error is less only. Okay, error due to the mutual inductance between two coils will be less at power frequencies. Next one is errors caused errors caused because of connections. Because of connections. Errors caused because of connections. Okay, normally we have two types of connections in wattmeters to measure power. Okay, uh, what are they? They are MC connection, LC connection. Okay, normally current coil in series with the load. Okay, pressure coil across the applied voltage, right? Okay, now this terminal will be M. M stands for mains. This terminal will be L. L stands for load. This terminal will be C. C stands for common. This terminal will be V. V stands for voltage. Okay. Now this is connection 1. Okay, connection 1. In connection 1, what we do is we join these two terminals. We join M and C terminals like this. Okay, MC are shorted. MC terminals are shorted. Okay, that's why it is MC connection. Coming to LC connection, okay, current coil in series with the load. Okay, now pressure coil and resistance in series with this. Okay, let V is the voltage applied across this circuit. Let V is the voltage applied across this circuit, right? Now let me indicate terminals. This is M. Sorry, this is M, L, C, V. Okay. Okay, in this connection 2, this is connection 2. Okay, in this connection we join L and C terminals. LC terminals are shorted. Okay, so we join these two terminals. L and C terminals are shorted. Okay, first we will look into this connection first. Okay, first connection is connection 1 is MC connection. I'll do one thing. Let me draw two circuits together in the same page. First one is MC connection. This is what is MC connection. Coming to LC connection. Okay, LC connection. This is LC connection. This is MC connection. LC connection. Okay. V is the applied across. V is the voltage which is applied across the circuit. Okay, phase neutral. Phase neutral, right? Okay, this is what this is. LC connection. Okay, this is LC connection. Okay, now what is the power indicated by the wattmeter if I use this connection? Okay, now power indicated by wattmeter is equal to, see here, this pressure coil circuit is connected across applied voltage. So voltage across this pressure coil circuit is nothing but voltage across current coil and voltage across the load. Okay, this is load. Let I is the current flowing to the load. Okay, so voltage across this pressure coil circuit is equal to voltage across current coil and voltage across load. Okay, then you're going to get the voltage drop across this current coil. You're going to get the voltage drop across this current coil. So power indicated by the wattmeter will be equal to power consumed by the load, power consumed by the load plus power loss in current coil, so power indicated by the wattmeter will be equal to, which is equal to power consumed by the load plus I square RC is the power loss in the current coil. Okay, now coming to this connection, what is the power indicated by the wattmeter? Power indicated by the wattmeter, which is equal to power consumed by the load, power consumed by the load plus, okay, now see here, the current which is flowing through this is IP. Okay, the current which is flowing through this is IP. The current which is flowing through the load is I. Okay, now the current which is flowing through this is I plus IP. I plus IP. Okay, here this carries only I, but voltage across this will be equal to voltage across this plus voltage across this. Here this carries not only load current but also the current which is flowing through this pressure coil circuit. It is carrying both currents, the current which is flowing through the load as well as the current which is flowing through the pressure coil circuit, right? Then the total current which is flowing through this will be I plus IP. So power indicated by the wattmeter will be equal to power consumed by the load and power loss in the pressure coil circuit. Okay, so power loss in the pressure coil circuit plus power loss in the pressure coil circuit. Fine. Okay, which is equal to PL plus V square by RP. V square by RP or IP square into RP or IP square into RP. Okay. Now, if the load current is high, okay, if load current is high, this power loss will be more. Okay. So, if load current is less, if load current is low, okay, what about the power loss? Power loss will be less. Okay. So, for small load currents, For small load currents, this power loss will be less. This power loss will be less. Okay, so this connection is preferable. Okay, power indicated by the wattmeter nearly equal to the power consumed by the load for small load currents. Okay, for small load currents, this power loss will be less. Okay, if it is less means almost the power indicated by the wattmeter is nearly equal to power consumed by the load. Okay, so for small load currents, this connection is preferable. Okay, coming to this connection, if see IC is equal to I plus IP here. Okay, if IP is equal to IC minus I. Okay, if this current is more means this will be less. Okay, if this is less means power loss in pressure coil circuit will be less. That is V square by RP will be less. So if the load current is high, for high load currents, this connection is preferable because if this is more means less amount of current will be flowing to this circuit. Then when compared to this load current, this will be small value. When this is small value means power loss in this pressure coil circuit will be small. If the power loss in the pressure coil circuit is small means power indicated by the wattmeter is nearly equal to the power consumed by the load. Okay, so this connection is preferable for high load currents. For high load currents. So for light load currents, for small load currents, this connection is preferable. For high load currents, okay, if the load current is large or if the load current is high, then this connection is preferable. Okay, now here in MC connection, this current coil is connected on load side. Okay, here in LC connection, pressure coil is connected on load side. Okay, you can say like this: current coil is connected on load side. Here, current coil is connected on supply side. Okay, if the current coil is connected on load side, then the type of connection is called MC connection. If the current coil is connected on supply side, then the type of connection is called LC connection. Okay. Okay. Anyhow, power loss in this current coil will be low. Okay. So we have a compensation for pressure coil power loss in pressure coil. Okay, we will look into that compensation for pressure coil power loss or power loss in the pressure coil a later point of time when we discuss about low power factor wattmeter. Okay, no compensation is required for power loss in current coil. Okay, so we require compensation for power loss in pressure coil. Okay, we discuss about that compensation for power loss in the pressure coil when we discuss about low power factor wattmeter. Okay, this is for light load current, this is for high load currents. This connection is preferable for high load currents. This connection is preferable for small load currents. Okay. Next one is eddy current errors. Eddy currents are induced in the solid metal parts, solid metal parts of the instrument, and within the thickness of conductors, as current coil is massive to carry considerable amount of current. So within the thickness of the conductors also, eddy currents will be induced. So eddy currents will be induced the solid metal parts of the instrument, and within the thickness of conductors, within the thickness of conductors. Okay, because of the current which is flowing through the, because of alternating magnetic field of the current coil. Okay, alternating current is flowing through the current coil, so alternating magnetic field will be produced in the current coil. Because of that alternating magnetic field, eddy currents will be induced in the solid parts of instrument as well as within the thickness of conductors. Anyhow, this error is less only. Okay, eddy current error is less only. Okay, coming to the next error. Next error is stray magnetic field error. Magnetic field error. What is mean by this stray magnetic field error? Error due to the effect of external magnetic field upon the internal magnetic field of the instrument is called stray magnetic field error. Okay. Uh, some external magnetic field. Okay. Inside of this instrument, weak magnetic field is present. Field is present. Okay. Weak magnetic field is present. Okay. So external magnetic field may show effect upon the internal magnetic field of the instrument, as weak magnetic field is present inside of this instrument. Okay, so this error is more in this instrument when compared to other instruments like MI instrument and PMS instrument, because it is having very weak magnetic field. Okay, instead of this instrument, very weak magnetic field is present. Okay, so in order to eliminate this error, in order to reduce this error, these instruments are shielded. Okay, these instruments are even my instrument is also shielded. Okay, against the effect of this stray magnetic field error. Okay, against the effect of this stray magnetic field. Okay, MI instrument is shielded as well as this dynamometer type instrument is also shielded. Okay, these instruments are shielded. Okay, they are shielded to avoid the stray magnetic field error. Okay. Okay, the next one is errors caused by vibration of moving system. This error is found occasionally on alternating currents. Okay, in this instrument, this error is found occasionally. Okay, we know, right? Torque is directly proportional to AC power. Okay, different torque is directly proportional to AC power. Okay, means the torque on the moving system varies cyclically with a frequency which is twice that of voltage. Okay, because deflecting torque is directly proportional to AC power. Okay, so the frequency of TD will be twice that of the frequency of voltage. Okay, because TD is directly proportional to AC power. as DC is direct proportional to AC power, okay, frequency of power will be twice that of voltage, right? Okay, so that's why frequency of deflecting arc is twice that of the frequency of applied voltage. So in this instrument, we're going to have a pointer, okay, pointer, spring, okay, spindle, and pressure coil. All are moving elements. Okay, moving elements present in the instrument. These are all the moving elements. Okay, every object has its own frequency. Okay, this object has its own frequency. This is also having its own frequency. This is also having its own frequency. Again, this that is also having its own frequency. Pressure coil circuit, moving element, okay, moving coil. This is what this is, moving coil. This is also having its own frequency. Okay, a pointer, spring, or some other parts, movable elements which are present in the instrument have their own frequencies called natural frequency. This has its own frequency called natural frequency. Okay, so if the frequency of torque pulsations matches the frequency of pointer or spring or spindle, then moving system will vibrate with more amplitude, with high amplitude. Okay, that is called resonance, right? Resonance occurs when mechanical resonance occurs. Resonance occurs when frequency of torque pulsations matches the frequency of any one of these objects, then resonance occurs. Okay, you know, right? You take glass, you produce sound waves near to this glass. Okay, you increase the frequency of these sound waves. Okay, at one particular point of time, this glass will break. When glass breaks, okay, frequency of sound waves matches the frequency of glass, then glass breaks. Every object has its own frequency called natural frequency. Okay, so this is having natural frequency. Natural frequency. Okay, the frequency of glass, nothing but natural frequency, matches the frequency of sound waves, then this glass will vibrate with more amplitude, then glass breaks. Okay, if the frequency of sound waves matches the frequency of glass, then glass will vibrate with more amplitude, then uh, time comes to break the glass. Okay, the glass will break when this frequency matches the frequency of this. Okay, similarly, when the frequency of torque pulsations, because of torque, moving system will be moving, right? Okay, torque pulsations. Okay, so frequency of torque pulsations matches the frequency of moving system moving system or matches the frequency of any one of these moving elements, then they vibrate with more amplitude. Okay, then moving system would vibrate with more amplitude, higher amplitude. Okay, then that more amplitude vibration, then vibration with more amplitude disturbs the position of the pointer. Okay, disturbs the position of the pointer. So I should avoid this vibration of moving system. Okay, so in order to eliminate this error, okay, these moving elements are designed in such a way that the frequency of torque pulsation will be far away from the frequency of moving elements. Okay, if the frequency of torque pulsation is far away from the frequency of moving elements, then resonance will not happen. Resonance will not happen, then you will not get vibration of moving system. Then position of the pointer will not get disturbed. Okay, and the last one is temperature errors. Okay. Power indicated by the wattmeter may get affected upon the change in temperature. Okay, change in the room temperature. Okay, so if temperature changes, okay, with the change in temperature, resistance of the pressure coil circuit will be changing. Resistance of the pressure coil circuit will be changing, as well as resistance of the pressure coil will be changing, as well as uh, stiffness of the spring will be the spring springs will be changing. Okay, suppose if I increase the temperature, what will happen? If I increase the temperature, with the increase in temperature, resistance will be increasing. Resistance of the pressure coil circuit will be increasing, because we use conductor. Conductor is having positive temperature quotient of resistance, right? With the increase in resistance, current will be decreasing. With the decrease in current, TD will be decreasing. Now, coming to the stiffness of spring, with the increase in temperature, stiffness of the springs will be decreasing. If it is decreasing means TC will be decreasing. If TC is decreasing means TD will be increasing. Okay, here TD will be decreasing, here TD will be increasing. Both are opposite effects. And both effects will get nullified. If I add an alloy to the pressure coil circuit. Okay, by maintaining the ratio of copper to that alloy will be 1:10. Okay, pressure coil circuit. Okay, in pressure coil circuit, the ratio of copper to alloy is 1:10. If I maintain this ratio, these two effects will get nullified, as these two are opposite effects. Okay, so they get nullified if the pressure coil circuit is composed of copper and alloy in the ratio of 1:10. Okay, coming to some more errors which are present in this instrument. Frictional error. Anyhow, pressure coil is having more number of turns in this instrument. So anyhow, this frictional is depending upon the ratio of torque to weight, right? It is the ratio of torque to weight. If the torque to weight ratio is more, means frictional error will be less. If it is more, means it is less, right? Whereas in case of this wattmeter, dynamometer type instrument, okay, weight of the instrument will weight of moving element. Weight of moving element. Moving element means pressure coil. Moving element is more, then frictional error will be more. It is more only. Frictional error is more frictional error. Okay. Frictional error, order of frictional error. Okay. EMMC or dynamometer type instrument. EMMC having more frictional error, and next PMMC, then MI. Okay, coming to the next error, hysteresis error. This error is almost zero. This error is almost zero. Why? It is zero because here in this instrument we use air core. We will not use any um, iron related materials. Here we use air core. Okay. Current coils are air cooled. Okay. That's why hysteresis error is zero. Okay. Except frictional error. Okay. If you take frequency error, okay, order of frequency error, or temperature error, or stray magnetic field error, stray magnetic field error, okay, or order of accuracy. Okay, if I take any error, the order will be like this. EMMC instrument will be having more. Okay, it is having more friction error, more temperature error, more stray magnetic field error, less accuracy. Okay, I will come back to this accuracy. So now the order will be like this: EMMC, MI, PMMC. Okay, this will be having more frequency error, more temperature error, more stray magnetic field error when compared to other instruments. Then after MI having more frequency error, more temperature error, more stray magnetic field error when compared to PMMC. This is the order. Coming to the order of accuracy, accuracy, order of accuracy. Order of accuracy will be like this. PMC is having more accuracy. It is more accurate than MI. MI is more accurate than EMMC, electromagnetic moving coil or dynamometer type instrument. Okay. This is the order of friction error. Okay. This is having more friction error when compared to PMC. PMC is having more friction error when compared to MI. Okay. This instrument is having moderately low friction error when compared to PMC. Okay. Coming to hysteresis error or hysteresis error. Hysteresis error. Anyhow, EMMC is having no hysteresis error. Error is almost zero. Okay. So MI instrument is having more hysteresis error than when compared to PMC. Okay, and EMMC in EMMC almost zero hysteresis error. Okay, thank you.